Thank you again. Now we will go to our next presenter, Dr. Sylvia Biscoveanu, NASA Einstein Fellow at Northwestern University, working on using gravitational wave data to understand the properties of compact object mergers, their electromagnetic counterparts, and stochastic gravitational wave background. I will stop there because this is beyond my level of comprehension, and I hope that she will deliver a layperson presentation. Thank you so much for joining us. Sylvia?
Mulțumesc foarte mult pentru invitație. Can you hear me and can you see my screen?
Yes, we can.
Great. Eu sunt acum, de fapt, în România pentru sărbători, așa că îmi pare foarte bine că am putut să mă conectez virtual. And I'm very grateful for the opportunity to tell a bit of research, which focuses on listening to the universe with gravitational waves, and also in parallel about my career trajectory, which has taken me from music. So about 100 years ago, Albert Einstein finally came up with a theoretical explanation for the force of gravity in his theory of general relativity. And basically, in his theory, he posited that space-time is like a malleable fabric that warps in the presence of massive objects. So the space that we occupy is affected by the presence of massive objects, and the trajectories of these massive objects are equally affected by the warping of this space. And you can see here an example of what this warping might look like in 2 dimensions, because we cannot visualize the full 4-dimensional space-time grid. Here, for example, the Earth in orbit around the Sun, and the warping of this space-time fabric due to both of these massive objects. So this was in 1915, the theory of general relativity. So 1 year later, expanding on his theory, Einstein predicted the existence of a phenomenon called, which are ripples in this space-time fabric caused by the acceleration of extremely compact astrophysical objects. You can see here 2 of these compact objects in a binary system orbiting around each other, getting closer and closer together until they eventually merge, and they emit these space-time ripples. So these are similar to the ripples that you get when you throw a rock into a pond, for example. And eventually these ripples propagate out, and we might be able to detect them here on Earth. So what are these compact objects that can potentially produce these gravitational waves? Well, one kind of compact object is called a neutron star. And these are very evolved stars that are made entirely out of nuclear matter. So they're made mostly out of neutrons. So neutrons as a particle were in 1925. And less than 10 years later, it was theorized that these stars made almost entirely out of neutrons should come to arise as the dead cores of stars that are initially 9 to 25 times more massive than our own sun. So when these massive stars reach the ends of their lives, they undergo a big explosion, leaving behind one of these neutron stars. And these objects are remarkable because they're actually so dense that their entire mass, which is greater than the mass of our sun and our solar system, into a sphere, the radius the size of a city. So you can see here a visualization of one of these neutron stars compared to, maybe you recognize, New York City. So here you can see the island of Manhattan, and then you have Queens and Brooklyn on this side. So one other possibility for one of these compact objects that can produce waves is a black hole. So these are actually the densest objects in the universe. They are more dense than neutron stars. And until about the 1960s, they were basically considered a curiosity. So for the first 50 or so years, when the mathematical properties of these objects were known to exist, we didn't think that they could actually exist as astrophysical objects in the universe. But in the 1960s, it was the first time that they were described as a region of this space-time fabric with curvature so extreme that not even light can escape. And you can see here a visualization of one of these black holes, aptly named. There is some event horizon beyond which we cannot see anything because the gravitational pull of this object is so strong because of how extreme the space-time curvature is that we cannot see anything horizon. The light in this region simply cannot reach us. It cannot escape the pull of gravity. So these are the two kinds of objects that we think, if we observe them in these binary systems, they are emitting gravitational waves. So as we saw earlier, it's possible that these gravitational waves propagate out and reach us here on Earth. And the effect of gravitational waves on Earth is demonstrated in this visualization here. Basically what happens is it stretches space-time in one direction and it squeezes it in the other direction. This is obviously a extreme exaggeration of the effect because we are constantly being bombarded by these gravitational waves, but we don't feel them. And we don't feel them because this stretching and squeezing of space-time is so small that it's actually less than the diameter of a proton. So we need extremely sensitive instruments in order to be able to perceive this effect. And, by measuring these gravitational waves, we hope to learn about the lives of these massive stars that produce these compact objects, and we hope to learn about the fundamental nature of gravity in order to understand basically this fundamental force that governs our universe. And I should mention the concepts behind the technologies for detecting these gravitational waves were developed extensively starting in the 1970s. So in the 1990s, concepts were already mature, and there was a proposal to build a detector that would be sensitive enough to detect these space-time disturbances called LIGO, the Laser Interferometer Gravitational Wave Observatory. So basically how these works is you have a giant L-shaped laser, and at each end of the arm of the L is a mirror that is suspended, and so it can move. And so when a gravitational wave passes by, it will stretch one arm of this interferometer and squeeze the other. And so the mirrors will move and this laser light will basically get out of phase. And so when it recombines, we can see a characteristic interference pattern that tells us that a gravitational wave has passed by. And so these instruments were funded by the US National Science Foundation in 1994. This is when construction began, and the initial phase of the experiment began taking data in 2002. So I told you also tell you about my career path in parallel. I am the daughter of Romanian immigrants. I was born in Philadelphia. My parents moved to the US in 1991. And I did not always dream of being a physicist. So until my final year of high school, I actually thought I would be a professional violinist. I started playing violin when I was 5, and this is how I spent all my weekends and my free time practicing when I was younger. But we've talked a lot about the importance of mentors, and through discussions that I had with a very important mentor early on in my life, my violin teacher, I decided that I would be better served to go to university to pursue a more academic career rather than trying to struggle as a musician, as it is extremely competitive. So being from Pennsylvania, I went to university at Penn State. And given this pretty recent change of heart about my career trajectory, I arrived at the university completely undecided about what I wanted to study. And so this time in my career was extremely important and is basically the reason why I am where I am today. And in particular, I had two very important mentors, my academic advisor, Professor Richard Robinette, who you can see here in the white beard. So he was the one, I had a vague interest in physics and I stumbled into his office and he encouraged me to take all the right classes and to actually get in touch with and start research with Professor Miguel Mostafa, who you can see on the right here. And I was able to conduct research in a slightly different field in undergrad in astroparticle physics. I worked with an international collaboration in Argentina, and so I got to travel and see the instruments there. And I am incredibly grateful for the support of these two mentors and the way that they took me basically from not even realizing that professional physicist is something that I could do as a career to bringing me to where I am today. So shortly after I started university, these LIGO instruments completed a phase of upgrades to their sensitivity. And during their first stage of operation, they actually did not detect any gravitational waves. But following these upgrades, basically as soon as they turned back on again at their upgraded sensitivity, they immediately detected gravitational waves for the very first time. And you can see and hopefully hear the signal here, what this looks like. So we can turn our gravitational wave signal into a sound clip. This is why we say listening to the universe, because gravitational waves are like the music of the cosmos. So this is what this first signal looked like in the two LIGO instruments. So it was determined that this first detection came from two black holes about 30 times the mass of the sun that smashed together 1.4 billion light years away. So this was in 2015. And I actually joined the LIGO scientific collaboration just a couple months before this first direct detection for a summer undergraduate research project in Australia. So after I finished my undergraduate studies, we've already heard a lot about the Fulbright program. I wanted to go back to Australia and to continue my research with my mentors there. So I got a Fulbright postgraduate grant to spend 10 months in Australia in between my undergraduate and PhD studies. And I worked with Professor Eric Thrain, who I continued to collaborate with throughout my PhD. And even now, this is me with a kangaroo, because it wouldn't be a trip to Australia if you didn't get a kangaroo picture. But this experience really shaped my perspective on the kinds of large international scientific collaborations that are increasingly becoming the way that we conduct astrophysics research. You know, we're no longer working in the regime of the lone genius like Einstein. It often takes a huge international team of thousands of people in order to make a significant discovery. So it was really important for me to be able to experience how research in physics is done in a different country, and to incorporate some of those methods and means of collaboration into my research. So for the sake of time, I'll go through this very quickly, but in 2017, we had another very important gravitational wave detection. This time it wasn't two black holes merging, it was two neutron stars. And shortly after this neutron star event, gravitational waves, and specifically the three key players in the LIGO instrument and the theory behind the gravitational waves that we were detecting, won the Nobel Prize in Physics in 2017. So in 2018, I began my PhD at MIT. And I was very fortunate to get funding for my PhD from the Paul and Daisy Soros Fellowship for New Americans and the NSF Graduate Research Fellowship. So the Paul and Daisy Soros Fellowship is specifically for immigrants and children of immigrants pursuing graduate study in the US. It's a wonderful program where you really become part of a community. So they don't just give you money. There are reunions every year, and you really feel connected to this community of people that have, you know, similar experiences coming from an immigrant background and similar values to you. So this was a really important part of my PhD experience. And then the NSF Graduate Research Fellowship is for students in STEM fields. This is a more standard, similar to an NSF grant. So my thesis was titled From Black Holes to the Big Bang, Astrophysics and Cosmology with Gravitational Waves. And of course, I had invaluable mentorship from my thesis advisor, Professor Salvatore Vitale. And then just to conclude, where are we now? So I am currently a NASA Einstein postdoctoral fellow at Northwestern University in Chicago. And next fall in September 2025, I'll be starting as an assistant professor in the Department of Physics at Princeton. And we have now detected over 200 gravitational wave candidates with the LIGO detectors and their sister instruments, Virgo and Kagra. So you can see here the cumulative number of observations as a function of time. And so I'll just leave you by saying that the future of gravitational wave astronomy is loud. And thank you again for the opportunity.
Thank you, Sylvia. We're so incredibly proud of you and what you've achieved in your very young career, I mean, very impressive career. In fact, I'm so impressed. I think I'm thinking of registering my two years and 9 months old daughter to violin classes just to follow your trajectory. I hope you'll be her mentor.
Excellent. Thank you again for the invitation.
Thank you for this terrific presentation. We're so proud of you.